In this video, we are going to use the first-letter theorem to prove that in any system whose Lagrangian is independent of time, there is a constant of motion that we will call the energy, and that will coincide with the energy that we derived in a previous video using the standard techniques. In doing so, we will show that the conservation of the energy is also related to an invariance of the action. So an invariance under which transformations? In the simple setting in which we have proved the first-letter theorem, we just consider variations of the variables xi of this form. Okay, I write this alpha here just to stress the fact that we are considering this particular kind of transformations and not generic transformations of some kind. Sometimes I do it, sometimes I don't, but this is not essential. It is essential that we will impose at some point this condition. Okay. So now let's consider an arbitrary system and let's see what the variation of the action is. Under this transformation, this is what I write delta alpha of S. Since these transformations do not involve time, as usual, this is just delta alpha of L. And okay, we know how to do this. This is the partial derivative with respect to xi, delta alpha xi, plus the partial derivative with respect to x dot I, delta alpha x dot I. Again, since we are dealing with transformations that do not act on time, we know how to deal with this delta alpha and then the derivative, because they commute. They commute, and we can write dt delta alpha xi. And now I can use this particular form of the transformations and replace them in the formula. I will get here alpha x dot I, and here I will get alpha x double dot I. So a common factor of alpha that multiplies partial L with respect to xi, x dot I, plus partial L, x dot I, x double dot I. This is nothing but the derivative of the Lagrangian with respect to time minus the partial derivative with respect to time. Okay, so this is because of the general formula, the total derivative of the Lagrangian. And if we use the condition that the partial derivative of L with respect to t is 0, because there is no manifest dependence of the Lagrangian on t, this term vanishes, and we find that the variation of the action is a total derivative with respect to time. Okay, these were the conditions of the generalization of the first-letter theorem that we found in the previous video at the end. So initially we demanded exact invariance of the action, but later we saw that they could be relaxed to invariance up to a derivative with respect to time. This is the most general, more general statement, and we can directly apply the Noether theorem here. Instead of applying the formula, I remind you that this can be written also, and this is how we do it, in this way. Plus a total derivative L x dot I delta alpha xi, and these two things are then equal. So taking this into this side, we find that the total derivative, okay, of alpha, because this is just alpha x dot I, alpha partial L x dot I minus L is equal to minus the equations of motion alpha x dot I. I am also substituting delta alpha xi there. Okay, this is true for any alpha, so the alphas can disappear. Then, if the equations of motion are satisfied, this quantity that we called h is conserved. Okay, so this proves the relation between the conservation of the energy and this symmetry of the action. Symmetry up to a total derivative that takes place in any system whose Lagrangian is independent of time. Now, you probably have heard that the conservation of energy is associated to invariance under translations of time. Indeed, these transformations that I have written here for the xi's are related to the to time translations, but this relation is a bit more complicated. So if you are ready for something, for a more complicated version of this proof of the conservation of the energy, you can continue watching this video. Otherwise, you can go to the next one, because this is maybe a bit too advanced for the level of this course. So here it goes, the more complicated story for those that want to keep watching. And want to learn the reasons why things really happen. Okay, the first thing that we are going to do is to make a more precise definition of these variations. Okay, we just said that these delta xi's are infinitesimal transformations and so on, but how do we really define these delta xi's? We have to define really two things. Let me define this delta tilde xi in this way. And in fact, for any function of time. Okay. So we take these xi's in some time coordinate t prime, and they will have some expression xi prime, and we just subtract xi in the time coordinate t. Okay, these xi's they behave as scalars, in the sense that as functions. This means that if you want to find this xi prime of t prime, the only thing that you have to do is to replace t by t of t prime in the expression of xi. Okay, so xi prime of t prime is nothing but xi of t prime, just a change of variables, nothing else. But because xi is a scalar function, and it behaves this way, what happens is that for the same instant of time, okay, expressed in t or in t prime, xi has the same value. Whether it is xi or xi prime, it will have exactly the same value. If it has the same value, this delta tilde, which is the total variation of xi, we find it to be the total variation, just vanishes. Then I am going to make another definition of variation, which is sometimes called variations at a point, and that are, so this was a definition in fact, and this is another definition. We just consider for this delta the change in the form of this function, but now we take it at the point at the value of t, okay, in terms of t. Okay, this is a different thing, and delta tilde and delta are related in this way. So here I can always expand xi prime of t prime if t prime is t plus an infinitesimal piece, then xi prime of t plus delta t minus xi of t, and then I expand this as xi prime of t plus delta t dt x prime I minus xi of t. Now x prime I, if the difference between t and t prime is infinitesimal, will also be the difference between x prime I of t, and xi of t will also be infinitesimal. So if we multiply it by delta t, this difference will be of second order, and we are always staying at first order in variations. This means that I can eliminate this prime, okay, or replace x prime I by xi, and at this order this is correct. Okay, now these two terms are what we have defined as delta xi, and this is just x dot I. Okay, so the moral is that delta xi, delta tilde, and delta are related in precisely this way. And for this particular, this is completely general, even if xi was not a function, but if it is a function, we have seen that delta tilde is 0, because the property of scalars or functions is that they take the same value at the same point, even if we express this point in a different coordinate. Here we are talking point means a given instant of time. Okay, so in this particular case, delta xi is equal to minus delta t x dot I. Then, if delta t is is constant, and I call this constant minus alpha, then I find these transformations: alpha x dot I, which are the transformations that I considered at the beginning. These transformations are related to constant shifts of time, infinitesimal constant shifts of time, okay, by this constant. Now for constant shifts of time, the x dots I are also functions. This means that the total variations are 0. And using the same reasoning to get that delta x dot I is equal to minus delta t x double dot I, and you find that x delta x dot I is equal to alpha x double dot I, which is also the formula that we have used. So this is where these transformations that we labeled with alpha come from. And if we consider these deltas not the total variations, then we can ignore the delta t's and the variations of time. However, we can consider the total variations, and rederive this conservation of the energy and the Rutherford theorem using the total variations. So let's see what happens if we consider the total variations of the action. Now, these total variations include variations of the time coordinate. So we have delta t L, okay, plus dt delta alpha L. I don't write delta tilde on t because I mean the variations of t always involve the variations of the coordinates, so there is no difference between delta and delta tilde. It doesn't make much sense. Okay, for these particular transformations, delta alpha t is constant, so its differential is 0. And we can study the variation, the total variation of L. And using the same expressions we use, then we have partial derivatives and variations x dot I plus again I can write alphas everywhere because we are dealing with this particular kind of transformations. And see, for these transformations we for the properties of the xi's these two terms cancel. And this transformation will not vanish, the transformation of the action will not vanish unless, or will not vanish even up to a total derivative, unless the partial derivative of the Lagrangian with respect to time is 0. Then we will have that the total variation of S is 0. And here there are no total derivatives. If this happens, the total variation, the symmetry is exact. Now we take this same total variation of the action and we are going to rewrite it in a different way. This is how you obtain identities. You just take the same expression and or the same quantity and you rewrite it in different ways. And okay, this variation is just what we wrote here, but ignoring the partial derivative of t because we have assumed that it is 0. Otherwise we don't have a symmetry. So we have this variation. Okay. Of course, this is 0. We know it. Okay, but we are going to rewrite it in a different way. So we apply this generic relation between tilde and untilde variations. And this has this expression. Delta xi plus delta t x dot I plus partial L respect to x dot I delta x dot plus delta t x double dot I. Okay, these are the familiar expressions that we have found many times, so we can deal with them in exactly the same way. Let me write everything in this order. So we have partial L with respect to xi delta xi plus partial L with respect to x dot I delta x dot I plus, and now I have delta t, and here partial L with respect to xi x dot I plus partial L partial x dot I x double dot I. Okay, now if we follow the standard steps, we know that this is going to give us nothing but the equations of motion times delta xi plus a total derivative of the form delta xi. And then we have this additional term, This additional term is just the derivative of L with respect to t. Okay, because the only term which is missing from this total derivative is the partial derivative of L with respect to t, which by assumption is 0. So we can write plus delta t L. Okay, and we get, because this is 0, okay, let me write this as we have found it. This is minus delta t x dot I. We find this identity. Here again, write exactly the same, minus delta t x dot I. The integrand has to vanish as usual, and this integrand and this relation you can write like this, and overall minus delta t, which multiplies this identity partial L x dot I minus L equal to minus delta s with respect to xi x dot I. And because this is true for any delta t, we can get rid of the delta t, and we get this identity, which proves exactly the same as before, that h dot is equal to 0 if the equations of motion are satisfied. So this is a more maybe one more rigorous proof, more complete, but the most important part is that it shows that the original transformations that we consider are related to time shifts. So you can say that the energy is conserved when the action is invariant under translations, under time translations or time shifts. So now, as an example, we can, it is almost trivial to compute the value of h for a particle moving in an external force field, which is static and is given by a potential that only depends on the position x. So the Lagrangian is the kinetic energy minus this potential, and clearly it satisfies the conditions of this theorem. And now we compute the partial derivatives with respect to the x dot i's, and this is just m x dot I. So h is m x dot I x dot I minus a half m x dot I minus v, which gives 1/2 of m x dot I plus v. So kinetic energy plus potential, which is what you expect.